So, today I will be starting a new module, and that will be on electric and magnetic fields. You must remember that electric field and magnetic field are always around us, because light is always around us and radiation is always around us, and these are nothing but combinations of electric field and magnetic field. We have several times talked about these fields when we were doing optics. So, in this module I will be talking more fundamental things about these fields, how they are produced and what kind of effects they produce on charges or currents and so on and so forth. To start with, let me repeat the experiments that we used to do when we were kids in class say standard 6, 7, so on, charging by rubbing and then attracting small pieces of papers and all those things. So, I have some 2-3 experiments here. Let us first enjoy those experiments. So, the first one is let us take this plastic straw, and I have some pieces, small pieces of paper, and let me rub it with my shirt. So, I do it here, I just rub it once and bring this close to these paper pieces, and you see what is happening. You see what is happening. So many paper pieces have jumped and they are attracted to this straw. Let us do another experiment. I take this straw, I rub it here and place it on this bottle. So, bottle I am only using as a stand, and I place it here. I try to place it here, it is not easy because it is charged and it is jumping here and there. Okay, good. I take another straw, again I rub it and then bring it close to this first straw, and you see what it is doing. Okay, it is repelling. So, like charges repel, unlike charges attract, and a charge and a neutral object also attract. These paper pieces were neutral and this straw was charged, still there was an attraction. So, you have seen all these repulsion, attraction experiments. The starting point for discussing these electrical forces is the Coulomb's law, and that is, if you have two charges or two objects, let us say object A and object B, and you have charges placed on these objects, Q1 charge here, Q2 charge here, and the separation between them is, let us say, R. Charges are always placed on some objects, some material. So, here A and B, the sizes of these objects is much smaller, or it is assumed that it is much smaller as compared to this separation. That is important restriction. So, if that happens, then the force on say B due to A, electrical force, is given by force is equal to Q1 Q2 over 4 pi epsilon naught R square. And with proper direction, if this Q1 Q2, the signs are same, both are positive charges, both are negative charges, then this whole thing is positive and it gives me the magnitude of the force. and the direction of force on B will be away from A. In that case, it will be away from A. So, this will be the direction of this force. If this product is negative, one is positive charge, another is negative charge, then the direction will be towards A and the magnitude will be just magnitude of this. So, that is known as Coulomb's law. Everyone knows that is the starting point of any chapter on electrostatic. All right. What I want to emphasize is that this is essentially a two-step process. Force on B due to A, force on this charge due to this charge is essentially a two-step process. The first step is that this charge Q1 produces something called electric field. Okay. So, that is first thing. Charge Q1 produces electric field. And how much electric field, in which direction? So, the electric field is given by Q1 over 4 pi epsilon naught r square. And in which direction? If this Q1 is positive, it is away from A, away from that charge. If Q1 is negative, it is towards that charge. So, that is the rule for charge producing electric field. Of course, the charge should be stationary in your frame for quite some time. Those restrictions are also there, but in those conditions, electrostatics which we call, this charge produces this much of electric field. And not only at B, it produces electric field everywhere. Wherever you want, you can take a point and ask how much is the electric field produced by this there. If the charge is there, this Q2 charge is there in the field of Q1, that is the second step now, that this charge Q2 finds itself immersed in the electric field which is produced by this Q1, and this field exerts force on Q2. So, the force on Q2 comes in that second step. Force exerted by electric field on Q2, and that force is given by Q2 times E, and that force is in the same direction as E if this Q2 is positive, and if this Q2 is negative, then the force will be opposite to the direction of electric field. So, that is how, if you combine this one and this one, taking proper directions into account, you get this Coulomb's law. So, why to go through this tedious process when I could have said that fine, the force is given by Q1 Q2 by 4 pi epsilon naught r square and Q1 is exerting force on Q2. I still emphasize that it is a two-step process and one must understand this, because electric field is a real entity. Electric field is just like you have matter, you have field. The field is very much there, whether this Q2 is there or not, the field is there. When light comes from sun, what is coming? It is electric field which is coming, magnetic field which is coming. It is the electric field which exerts force on the atomic dipoles to do all that scattering and these things. So, that connection of force with electric field and the connection of electric field with the source charge must be well understood. If you want to know the force on this Q1 due to this Q2, the same procedure, Q2 produces its own field, and in that field this A finds that all right, field is exerting force. So, that is how it has to be done. Of course, the field produced by Q1 will not exert force on Q1, that you can argue from symmetry. If it is there, in which direction the force will be, because the field is in all directions starting from Q1. So, all those things are there. Now, a quantity related to electric field is electric potential or electric potential difference. In fact, this potential is a scalar quantity, and you can pick up any point in space and say that all right, the potential is defined to be 0, or we fix that this point will have 0 potential, that is our choice. And then at all other points you can ask what is the potential and how it is related to the electric field. It is, if you have an electric field here in this direction, suppose in this direction, there is a point, this is some point, and at this point you have some electric field, and you go a small distance along that direction of electric field. So, if you go a small distance here and you reach here, if suppose this point is say some point P and this is some point Q, and the separation is small, say dl, and you can put this vector also. So, we will say that this V at Q minus V at P will be minus E and into dl. If we are going in the direction of the electric field, just E into dl with a negative sign will be the potential difference, VQ minus Vp. That means, if we are going in the direction of electric field, the potential decreases, and this is the potential difference between these 2 points. So, this potential, this is another way of describing the same field. The same field, the same electric field can be described by giving this potential everywhere. If you know potential everywhere, you can always calculate what is the electric field. If you know electric field everywhere and you fix up potential at one point, you can describe what is the potential at other points. So, these are 2 different ways to describe that electric field. Now, it so happens that in laboratories, it is lot more easy to measure the potential differences than to measure the electric field. And the measurement of potential is very simple. This voltmeter can do that, or multimeter can do that. And you all know batteries, cells, these are devices to produce a particular potential difference, which we sometimes call voltage. So, you can have 1.5 volt battery or 6 volt battery or 9 volt battery. So, that means at the terminals, this mechanism inside that battery or cell ensures that at the terminals the potential difference will be that much. Okay, so let us do some experiment with measurement of this potential and potential differences. So, look at the apparatus that we have. We have a dish here, this is a dish, a glass dish in which I have put some water, okay. And then we have a battery here, we have a multimeter here, and we would like to do something with the potentials and potential differences in this. So, let us have a closer look to this apparatus. So, now you can see this glass vessel in which we have put an aluminum ring. This is an aluminum ring at the periphery, inner periphery, and we have this cell, 9 volt cell, and one end is connected on this aluminum ring here, and the other end is still free. This is a multimeter and it is set to measure voltages here, potential differences here. There are 2 ends, one end is again fixed at that aluminum ring. Okay, now I am putting this positive end of the battery at the center. You can also see there is a you can also see this is a paper on which this glass vessel is placed, and there are lines marked and circles marked. These circles are concentric, and at the center I am putting this positive end of the battery, and then the radii of the circles are 2.5 centimeter, then 5 centimeter, and then 7.5 centimeters. So, since the battery produces a fixed potential difference, the potential difference between this periphery and the center is governed by this battery. And now, we want to measure the potential difference between this aluminum ring and different points. So, we will take the 0 of potential at this aluminum ring. So, this is at 0, and this will be measuring the potential differences. So, first I will do the measurement on this inner circle at various places, 2.5 centimeters the radius. So, let me put it here, and what is there on the display is 4.3, 4.2, something like that. Somewhere else on the periphery of this inner circle, it's again around 4. 3.8, 3.9, somewhere here, yes, 4.2, 3.9, around 4 volts. Now, let me go to the middle circle, the other circle, radius 5.0 centimeters. So, let me put it here. This is now 2.2, around 2.2. Here on again almost the same, 2.3, 2.4. So, somewhere around 2.3, 2.4, 2.35. Okay. And then the bigger circle, last circle here, so 1.2 here, 1.2 here, 1.38 here, 1.35 here on that same 1.13. So, you see there is some difference, and the difference is very likely because this aluminum ring which is there is not really a circular disc, circular ring. So, you do have a D-shaped type of thing. So, distances are not exactly same, but nevertheless you can realize that if I am on a circle, the potential is almost the same, and go to other circle, again the potential is almost the same, although with a different value, and so on. So, you have this thing. So, if I do some mathematics with this, let us say for inner one I take the voltage, remember this is our 0. So, to be around 4, here it is around 4, then here it is around 2.4, and here it is around 1.3, let us say 1.3, we had 1.3, yeah, we had 1.34, 1.2. Since this is closer to the aluminum ring which has a variation in the shape, therefore, the differences are little more on the outer circle. So, let me write these things on the board and ask a question. So, what we had? We had a aluminum ring here which I assume to be at 0 potential. This I assume to be at 0 potential. Then in the middle I put that positive end of the battery. So, there is some potential, high potential here, higher potential here. And then I have a circle, and what I find is that on every point on this circle, the potential is same. This potential is same. If this distance is r, you can ask what is the potential V at this distance r, no matter in which direction. These potentials are all same. So, if I write V here and r here, we had three values, 2.5 centimeters, then 5 centimeters and 7.5 centimeters. So, r is in centimeters and V is of course in volts. And what were the values? Around 4, around 2.4 and around 1.3. You have just 3 points here. Of course, one can measure at many more points, but with these 3 points, can you guess what is the functional dependence of this potential on this R? As R increases, this potential decreases, that is fine. But what kind of dependence is this? Whether it is 1 by R type or 1 by R square type or some other functional form between this V and R, try to guess.